We now get to the last section on this large unit on rotations. This is a brief dive into the beginning sections of chapter 12. Okay, chapter 12 overall is concerned with what is called equilibrium. An object in equilibrium is at rest with respect to an inertial reference frame. So it's the physics of an object that is at rest with respect to an inertial reference frame. An object in equilibrium is at rest with respect to an inertial reference frame. This forms the basis of a branch of mechanics that is called statics. Statics is concerned, once again, with the physics of an object at rest. Now, I'm being a little bit facetious about this when I describe it, but it's ultimately extremely important when you're talking about mechanical engineering, such as, for example, building a structure, building a building. You want your building to remain at rest with respect to an inertial reference frame. The last thing that you want, for example, is your building to topple over. So ultimately, it's an extremely important topic when talking about an engineering context. So it then ultimately forms the basis of what is called statics. Statics is essentially the physics of an object at rest with respect to an inertial reference frame. There are two conditions that are necessary in order for equilibrium to occur. The two conditions basically is concerned with Newton's second law, F equals ma. So then therefore, if an object is at rest with respect to an inertial reference frame, what can you immediately say about the sum of the forces exerted upon that object? They add up to zero. So the sum of the forces is equal to zero. In addition to that, the object doesn't rotate. So then therefore, with respect to an inertial reference frame, the sum of the torques that are exerted upon the object must also be equal to zero. That's the second condition that is necessary for an object to be in equilibrium. So the sum of the torques has to be equal to zero. The sum of the torques has to be equal to zero as measured with respect to any axis of rotation. Okay, you'll see what I mean when I set up a couple of numerical examples as we proceed, but let me begin actually with a really simple demonstration. Okay, my simple demonstration here involves this balance beam, like so, where right here I have an axis of rotation. And then I have these little tabs right here, for example. Each of these tabs has the exact same amount of weight. Okay, I'm going to go ahead and put one of the tabs here on the far right-hand side. That is my right-hand side of the balance beam, like so. And then where should I take one of these tabs and place it over here on my left such that ultimately the balance beam ends up being horizontal once again? Pretty obviously that's going to be over here on the far left-hand side like so. And then ultimately once again the balance beam ends up being horizontal. However, over here on my left, if I was going to place two tabs like so, where should I place the two tabs such that once again the balance beam here exactly levels out and is horizontal? If you're guessing halfway in between the axis of rotation and the end here on my left like so, you're exactly correct. That is like this. So let's examine this from a now qualitative perspective. Let's just examine the forces that are being exerted here on the balance beam when I include these tabs in these different locations. We'll then see how the sum of the forces has to add to zero and the sum of the torques has to add to zero. When I'm talking about the forces and the torques, I'm going to be talking about the forces and the torques exerted here upon the horizontal aspect of this, that is the balance beam itself. Okay, let me move this off to the side, like so. Okay, let me do some erasing here. Okay, and then we have this balance beam demonstration. Okay, so here's a simple drawing of the balance beam. There's first of all this stand, like so. Okay, and then right here is going to be the axis of rotation like this, and then right here is the horizontal beam like so. Okay, before I place tabs on the beam, what are the forces overall acting upon the beam itself? Well, we basically have two forces acting. We have, for example, is weight, which is exactly right here at the center of mass of the beam. That's obviously halfway here at the axis of rotation. So right here like so is an mg of the beam. But then in addition to that, as the axis here is being held in place by the structure here in purple, ultimately there's some sort of normal force upwards like so, just to cancel out the force of gravity. That is like this. I'll just call it the normal force N like so for simplicity. Okay, now of course those two forces are always going to be there and they're going to cancel out in this situation here as I now begin to put tabs on the right and left hand side of the beam. So now let's go ahead and start placing the tabs. So let's say that I place a tab over here like so, and I then therefore have an mg off to the side. Right here is this distance I'm going to refer to as L over 2, where the overall length of the red beam here is just L. Okay, pretty obviously I have to place one tab here on the left-hand side such that the beam balances out once again like so. Okay, then here's how we describe this in terms of the sum of the forces. Let me rename this here, by the way, just to distinguish it from these tabs. Let me call this M beam, like so, and then times G. Okay, now the sum of the forces has to add up to 0. So then therefore we have this normal force upwards, and then minus the weight of the beam, and then minus the weight of the two tabs, like so, is equal to 0. Okay, and then I first of all place this tab here on my right-hand side a distance L over 2 away. Let's then ask the following question. Where do I have to place this tab like so? That is this distance here. I'll just refer to it as x, such that once again everything balances out. This is where the torque calculation comes into play. Once again, the sum of the torques has to add up to 0. So let's go ahead and calculate the torques that are then exerted upon the red beam here, using this point right here as our reference. That is obviously the axis of rotation. So then therefore, is there a torque exerted due to the normal force N? No, because there's no moment arm, and R cross F is equal to torque. R is equal to 0 if the force is applied right here at the axis. Same thing with the weight of the beam itself. There's no torque due to the weight of the beam for the exact same reason. So the only torques, of course, that I have to worry about are the torques due to the two tabs. So let's take a look at this tab over here, which is our known in this situation. It's a distance L over 2 away from the axis of rotation. So there's the moment arm, L over 2 like so. Okay, here's mg. And now if you do R cross F like so, you end up with a torque vector into the board. Okay, I'll just call this tau 1, like so. And then in magnitude, tau 1 is going to be mg times L over 2 times the sine of 90 degrees. There's obviously a right angle here between L over 2 and mg. Okay, and then we've got our unknown, if you will. This tab over here on the left-hand side, a distance x away. So right here is its moment arm x, like so. Here's the little mg from that tab. Once again, this is a right angle. So if we do R cross F here, you end up with a torque vector out of the board. We'll make that one negative. We'll call this tau 2. And tau 2 we're going to say is negative mg times the distance x. And then once again, the sum of the torques here has to add up to 0. So mg L over 2 minus mgx is equal to 0. Solve for x. Obviously, x is equal to L over 2. Like so. So then therefore, think of it this way. It's almost as if we have two equations and two unknowns. The sum of the forces is equal to 0. The sum of the torques is equal to 0. And then therefore, we need the torque equation here to find the various distances. Okay, and then I adjusted the situation. So here's the second half of the demonstration. Let me erase this stuff here. Like so. Let me go ahead and redraw the stand again. Like that. Here's the distance L over 2. And then I took the two tabs. So the total weight is 2 mg. And then I placed it, for example, right here. Like so. And now let's go ahead and add up the forces. When we add up the forces, we once again have n minus m beam g and then minus 3 mg in this case. There's a total of 3 tabs that are being used in this version of the demonstration. But then we also have the sum of the torques. So there's no torque due to the normal force, there's no torque due to the weight of the beam once again, and now we take a look at this torque here again. Okay, this torque here again is the exact same value that it was before. We'll just write it as mg L over 2 once again. And then I have right here an unknown value we'll once again call x associated with this 2mg where I've placed 2 tabs. So then therefore we have our unknown moment arm x, right here is 2mg. So calculate the torque as r cross f, it comes out of the board once again, we'll make that negative. This torque here is negative 2mgx. And then we'll add it up. So we have this torque here from this over here on the right hand side, then minus this guy here, like so, and now let's go ahead and solve for x. So in doing so, I'm going to have here mgl over 2, mgl over 2, excuse me. There we go, equals 2mgx, and now solve for x. So mg cancels out like so, move the 2 down to the other side, and x is equal to L over 4, which is obviously halfway in between here and here, as we saw in the demonstration. So then therefore, once again, the condition that is necessary for equilibrium to occur is that basically you have 2 equations that add up to 0. The sum of the forces is equal to 0, and the sum of the torques is equal to 0. Okay, let's take a look at a couple of numerical examples. There are a few subtleties associated with these examples, and that's why I'm going to go ahead and take you through them. Let's take a look at the first of my 3 examples that I have here, and this involves a demonstration that I've set up over here on the right-hand side. I'll show you that demonstration in just a moment. Okay, let me go ahead and do some erasing here. Okay, let's go ahead and read the problem, write it down into your notes as always. Okay, a bar with a mass of 0.6 kilograms, so M is equal to 0.6 kilograms. Okay, it has a length we'll call L equal to 0.5 meters. It's hung from 2 spring scales as shown in my demonstration. Calculate what the scales read for the following situations. Okay, first of all in part A, let me move my file. Okay, in part A it says, the scales are positioned at opposite ends of the bar. So let me go ahead and tilt my phone so you can see what I'm referring to. Like so, and that's this situation here. So if you look at this situation, let me just go ahead and move my phone. If you look at the situation, I have that metal bar there that is hanging from 2 lengths of rope, 2 spring scales, and then attached to the attachment, the horizontal bar here towards the top. So what we're going to calculate is what the spring scales read for this situation. In this demonstration, the mass of this bar is about 0.6 kilograms, and its length is about 1/2 meter. And after I solve this portion of the problem, then I'll bring my phone over to the spring scales so we can see exactly what it is that they read. Okay, let me draw out the situation. This is for part A. Okay, so for part A, right here like so is my beam, and then we have now 3 forces exerted upon it. Okay, we have this force upwards, we're going to call T1. That's from the rope on this side, and that's of course what one of the spring scales is going to read. And then right here is the torque, or the tension from the other side. We'll call this T2. And then right here is the center of mass of the beam, so then therefore right here is its weight. And now let's just go ahead and add up the forces and set it equal to 0. So T1 plus T2 minus mg is equal to 0. Think of it this way, thus far there's 1 equation and 2 unknowns, T1 and T2. So then therefore I need another equation, and that's obviously going to be from the sum of the torques. It doesn't matter what you choose as the axis of rotation. The sum of the torques has to add up to 0 regardless of the axis, because once again the object is in equilibrium. But what you always want to do mathematically is choose an axis, a point if you will, to calculate the torques about, such that it makes the math easy to deal with. So here's then how I'm going to do that. I'm going to call this point right here the axis. Because if I call that point there the axis, is there going to be a torque due to T1? No, because there's no moment arm and torque equals R cross F. So then therefore I'm only have torques due to these guys over here on the right hand side of the diagram. Okay, so let's take a look at mg. Okay, its moment arm is from here to here. That's just 1/2 the length L. So we have here L over 2 like so. And then here's mg. You do R cross F, you end up with a torque vector into the board like so. We'll make that positive. It's mg L over 2. Okay, and then right here is a moment arm for T2. That's the length L, like so. And then right here upwards is the tension vector T2. So now if you do R cross F, you end up with a torque out of the board. We'll make that negative. So this is minus T2L, like so. And now we just add it up and set it equal to 0. Okay, so mg L over 2 minus T2L is equal to 0. Notice that the L's cancel out. And then therefore, when you do solve for T2 here, tension 2, you end up with 1/2 the weight of the beam. So then therefore, if T2 is 1/2 the weight of the beam, then pretty obviously T1 is also going to be 1/2 the weight of the beam. Like so. All right, so let's go ahead and calculate that because this is approximately what I do have with my spring scales. Let me grab my calculator. Okay, so the mass of the beam was 0.6 and then times 9.8, divide that by 2. And we end up here with a value of the force, T1 and T2, of about 3 newtons. It's like 2.94 newtons. T2 is the same value, 2.94 newtons, so about 3 newtons. So now let me go ahead and take my phone. I'm going to bring it over to the spring scales. Let's then see what they read. So bear with me here as I move the phone. Okay, so here's one of the spring scales, and you see there on the right-hand side of the scale that it's in terms of newtons, and yeah, it's 3 newtons. And then, oops, let me walk over here to the other side. Sorry about that. Like so. There's the other value, which is also at 3 newtons, like that. Okay, okay, let me bring my phone back. Okay, I'll be moving around here again in just a few moments. Okay, let me do some erasing here as we now get to part B of the problem. Okay, so now in part B of the problem, we're going to reposition one of the scales, okay? I'll set up and solve the problem, then I'll move the scale around, and we'll take a look at it. Okay, one scale is now positioned at one end, and the other is positioned halfway in between the center of mass and the end of the beam, or the end of the bar. Okay, so let's do it like this. Okay, right here is the beam once again. Here's its center of mass. Let's go ahead and put the T2 here again, like so. But now the T1 is positioned here, like this. And then right here is going to be the mg. Okay, once again, we'll consider this point here as the axis of rotation. And now what we're asked to solve for is T1 and T2 again, where the scale is going to read. Okay, this distance here is given to us as L over 4. This distance here is L over 2. So now the sum of the forces, when we add up the forces, it's the exact same expression as before, like so. And now let's once again go ahead and calculate the torques. So we're going to have no torque due to T2, where we once again consider this point here as our axis of rotation, and then here's mg. So right here is its moment arm, L over 2. Here's the mg, so you do R cross F like so, you get that torque into the board. We'll once again consider it positive. Okay, then right here is T1, its moment arm, you'll notice it's 3/4 L. So here's 3/4 L, like so. The torque of tension vector, is upwards. T1, let's make this 3/4 a little bit more distinct. Okay, now we do R cross F here. We get a torque vector out of the board. We'll consider that negative once again. So minus T1 times 3/4 L. Okay, let's add it all up and solve for T1. Okay, so mg L over 2 minus T1 3/4 L is equal to 0. Let's go ahead and do a little bit of canceling here. Let's cancel out the L's like so. Let's also cancel out a 2 here and here, thereby making this a 2. So now let's take this 3/2 T1 and move it to the other side. So mg equals 3/2 T1, and then solve for T1. T1 is going to equal then 2/3 mg. So it's going to be 2/3 the weight of the beam. Okay, so let's say 2/3, and then multiply that by 0.6 times 9.8, and this should work out to be about 4 newtons. It's like 3.92. Like so. Okay, and then let's go ahead and solve here for T2. So if I now solve for T2, that's going to be mg minus T1. So basically it's mg minus 2/3, it's 1/3 mg. Okay, so let's go ahead and figure out what that is. So 0.6 times 9.8 and then divide by 3. That comes out to be a little bit less than 2 newtons. It's about 1.96 newtons, like so. Okay, now let me go ahead and adjust my demonstration here. Let me do this. Okay, so here's T2. This is going to be the same as before, but now what we're doing is we're repositioning T1. So that's about roughly like that. Because right here is halfway in between. So this is the center of mass of the beam. So then therefore halfway in between is about right here, okay? Okay, now let me grab my phone. Let's go ahead and do this. Okay, so let's take a look at T1 first. Okay, T1 according to our calculations was a little bit less than 4 newtons. There we go. Like so, pretty good there on the right-hand side is the scale in newtons. And then the other one was about 2 newtons. There we go, like so, just about 2 newtons, okay? Okay, let me reposition the phone back. Okay, and then as I said, I do have 2 more examples here for us to take a look at. There are some subtleties associated with these examples. But let me go ahead and conclude this video here. At this point, we'll continue with a part 2 afterwards.